Hello, everyone. Thank you for watching our presentation on weekly supervised extractive summarization with attention. My name is Yingying Zhuang, and the work is jointly done with my colleagues Simi and Yichao here at Amazon. Automatic summarization systems are useful in many applications where they aim to create a concise version of large amounts of textual data, and much efforts have been devoted to automatic summarization in recent years due to an increasing need to access and digest such data. And one example is the need to build an automatic summarization system for Amazon customer service contacts. Here at Amazon, we receive hundreds of millions of customer contacts every year. An automated system that can extract relevant information from a customer agent dialogue will be especially useful in terms of providing context and highlights for contact transfers, escalations, and offline analysis. Automatic summarization systems typically fall into one of two broad categories, extractive and abstractive. Extractive summarization directly chooses the keywords or sentences in the original dialogue to derive high-quality information. For extractive summarization, training requires sentences and words being labeled as summary-worthy or not. And unfortunately, such labeled data are not available in our use case because we don't know which sentences and words should be extracted from the original dialogue. And the second option is abstractive summarization, which gives summaries of the dialogue by distilling the information and rewriting it in a concise manner. This approach can achieve great success by building a sequence-to-sequence neural network model. However, one main challenge with this approach in our use case is, again, the lack of available labeled training data, because agents at Amazon customer service are not required to write a paragraph of summary post-contact. Therefore, building a sequence-to-sequence abstractive summarization system is challenging in our use case. And those challenges essentially motivated our work here, which is to develop a general framework for automatic summarization for scenarios where there are no pre-labeled data. And in this paper, we focus on the approach of extractive summarization. We propose a model architecture that generates extractive summarization as a byproduct of a supervised learning tasks for indirect signals with the help of attention mechanism. This also intuitively makes sense because sentences and words that have provided strong signals to the downstream supervised learning tasks will naturally have higher attention weights and become good candidates for the summary. The architecture consists of a hierarchical attention network reader and a downstream ancillary prediction task that predicts the outcome for the indirect signal. The reader is constructed by four elements: a word encoder, a word level attention layer, a sentence encoder, and a sentence level attention layer. The downstream supervised learner is an ancillary prediction task for indirect signal. A byproduct of this supervised learning task is attention scores from the attention layers on both the word level and the sentence level. These attention scores reflect how strong of a signal they provide to the learning task, and therefore those with a higher attention score naturally are good candidates for the summary. For the learning, we explored three different types of prediction tasks suitable for different formats of indirect signals. The first one is a classification task. This works when the indirect signal is a categorical variable. When the indirect signal is a sequential output, the downstream supervised learner tasks, they take on the form of a recurrent neural network decoder, whose initial hidden state is set to be a fixed length of representation. However, one potential issue with this approach is the use of a fixed length vector could cause the performance deteriorates as the length of the input increases. And this will be showcased in our experiments. In order to address the bottleneck issue, the third supervised learner we explored is a sequence-to-sequence decoder with dynamic attention. The dynamic attention enables every position in the decoder to search through all positions in the input text for important information. And a distinct set of attention scores is calculated for each target word or sentence. And we use the summation of the total attention scores received for all output words to form the summarization. Lastly, we rank each sentence by its corresponding attention scores and also rank each word within a sentence by its corresponding attention scores. For extractive summarization, we select a preset number of highest ranked sentence and words to form our summaries. To evaluate the model performance, we set up experiments for the use case of Amazon customer service dialogues. We collected transcripts between customers and agents from over 1.6 million customer service chat contacts. We split the data set into approximately 80% for training, 10% for validation, and 10% for testing for the prediction task. For the classification downstream supervised learner, we use the indirect signal of customer issues and agent actions. In our data set, we group customer issues into 19 categories and agent action into 16 categories. For a classification-based model, we have one model that takes the concatenated customer messages as input and predict the category for the customer issue, and a separate model that takes the concatenated agent messages to predict the category for the agent action. For a classification ensemble model, we concatenated all utterances in the dialogue using the original order to predict a combined category. Since there are 19 classes in the customer issue and 16 classes in the agent action, there are 304 classes in total for the assemble label. And you're probably already thinking, as customer service contacts gets longer and more complex, the number of classes for this approach could grow dramatically, and a classifier model will no longer work. The sequence-to-sequence model will address these issues. For the sequence-to-sequence model, we directly predict customer issues as a sequential output, such as cancel order, or agent action, such as full refund. For the sequence-to-sequence based model, we predict customer issues from customer utterances and to predict the agent action from agent utterances, respectively. For the sequence-to-sequence ensemble model, the input is the concatenated utterances from both the customer and the agent, and the output is the customer issue concatenated with agent action, such as cancel order, for refund. Lastly, the sequence-to-sequence with dynamic attention model are set up in a similar fashion. For evaluation, we still need labeled summary data. We selected a random sample of 1,000 contacts from the testing dataset and had 2 professional human annotators to manually construct the label data. Specifically, they are asked to do the following tasks. First, for each contact, select the L most informative sentences from the dialogue and assemble them as the sentence level summary. L is set to be the ceiling of 20% of the total number of sentences in the dialogue. Secondly, for each of the L selected sentences, select K most informative words and assemble them as the word level summary. K is said to be the ceiling of 20% of the total number of words in this sentence. And these sentence level and word level summaries are the reference summaries for summarization methods. And we report the unigram overlap and bigram overlap as the metrics for informativeness, and the longest common subsequence overlap as the metric for fluency. The results table summarizes the Roche scores. It is clear from the table that among all models, the sequence-to-sequence with dynamic attention model outperformed the rest with a significant margin. It is also interesting to note that the scores for the base models are generally higher compared to the assembled model for classification and sequence-to-sequence. This is due to the fact that the transcripts in the base model are significantly shorter than the transcripts in the assembled models because they are from both the customer and the agent. Therefore, it is easier for the base models to compress all information into a fixed length vector. On the other hand, the assembled model outperformed the base model for sequence-to-sequence and dynamic attention. This is due to two factors. There is still valuable information in the agent's utterance to infer customer's issue, and valuable information in the customer's utterance to infer agent's action. And the second factor is sequence-to-sequence plus an attention model have great advantage in generating summaries with complicated and long dialogues. So in this figure, we compare the model performance for varying length of dialogues. We observed that the performance of the classification models and the sequence-to-sequence models dramatically decrease as the length of the dialogue increases. However, for the sequence-to-sequence with dynamic attention model, it showed no significant performance decrease, even with dialogues of 50 or more sentences. This confirmed our hypothesis that the sequence-to-sequence plus attention models were to overcome the bottleneck of a fixed length context vector in the basic encoder-decoder approach, which is critical for customer service as the need for a good summary increases as the length of the conversation grows. So in conclusion, in this paper, we proposed a novel approach based on ancillary labels and the attention mechanism to address the issues of conventional summarization approach where existing summaries are not available. We tested the proposed methods on Amazon customer service contacts and showed that this approach generated intuitive summaries, and the good performance did not decrease as the length of the dialogue increases. We left several challenges as open questions for future work. In our approach, we set the summary length threshold of selected sentences and words to be 20% of the total number. An alternative approach is to jointly learn the optimal number of sentences and words to extract during training. And in our work, we rank the sentences and words with their attention scores. In other words, we are more interested in the relative ranking rather than the exact scores. Therefore, another future work direction is to incorporate a ranking algorithm in the attention retrieval. Lastly, machine-generated extractive summaries may contain multiple sentences which are similar in meaning. It would be also worthwhile to explore a redundancy elimination approach that takes a machine-generated summary as a rough summary, identifies the semantic similarities between sentences in the summary, and further refines the summary by removing redundant segments. Thank you for watching.